Okay, so in week 1, part 2, we're going to take a look at facilities that we can use in the Pandas data frame module to obtain and analyze and display information about stock prices. Now, it's been some while since we talked about pandas and data frames. That was material from back in week 4 of the Python Programming Basics course. So if you're a little wishy-washy about pandas and data frames, you may wish to have a look at the part 1 lecture from week 4 in Python Programming Basics. And remember that on YouTube you can speed up the playback speed so you can review that material at a brisk pace as long as you can understand what I'm talking about. Okay, so let's get into this. So one way or one source of information about stock prices is Yahoo Finance, which has the advantage of being free, which is always a good thing. Now, I do want to mention that the interface that you use to talk to Yahoo Finance changes on a kind of random basis. And so each year, when I have talked about obtaining data from Yahoo Finance, I've had to change the details of how you actually go about doing that. So be aware that what I'm describing here in these notes is not permanent and guaranteed. This is something that you are going to have to look up, at least as far as downloading data. Now, once you have downloaded the data, analyzing the data is that material should be fairly consistent. So for now, what we want to do first is to install the Y-Finance module, which will enable us to get stock information and other financial information from Yahoo. And so what you'll do is go to your Anaconda terminal window and use this command pip3 install Y-Finance, and that should go out and find the correct Y-Finance module to install on your system. Once you've done that, you can start a shell running, a Python shell, and then you can try out these commands. Of course, you can do these commands as part of a program rather than doing them interactively, but I'm going to go ahead and do these interactively. So the first thing that we need to do is to import this Y-Finance module, which we're going to do as YF. So let me pull forward my Python shell, and we're going to do that. So I'm going to say import Y-Finance as YF. There we go. And next up, we're going to load some stock data using the YF download function. The first argument can be a list of stock tickers, and following that, we can specify the start and end dates for the range of trading days that we want to download. Now, I'm just arbitrarily using from January 1st of 2019 through January 23rd of 2019, but obviously you can pick a longer range of days, a more recent range of days, whatever. And in particular, we're going to take a look at the Apple, Cisco, Goldman Sachs, and U.S. Steel stock performance during that time. So let me go ahead and type this mess in. Actually, I can copy and paste it so I don't have to waste my time doing the typing. All right, so I'm going to copy and paste this from PowerPoint. Here we go. Okay, and we get some status information about things being downloaded. And now stock data is a Python data frame, as we can see. If we ask for the type of stock data, it is a pandas data frame, and we can display it in our shell by just typing its name, the variable name. Of course, in a program, you'd have to say print stock data. And here we go. All right, let me scroll up a little bit. Okay, so the three dots in here indicates that certain information is not being displayed. What we see here is that we do have the trading days as our row labels. Okay, now January 1st is a holiday, so our first trading day is actually January 2nd, and then down to January 22nd here. We specified January 23rd as our end date, but evidently yf.download is treating this like the end of a slice. So January 23rd itself is not included. And what we're seeing here is the adjusted closing price for the stocks, and then there's a bunch of stuff missing. We're seeing the trading volume for how many shares of the stocks were traded. Let's take a look at the index. Now that's going to be just the trading days, as we already saw. So stock, Get down here, stock data.index. This is going to be the row labels. And as we see, that's some number of days. And then for the columns, what we will get is something called a multi-index. All right, so let's see that. So stock data.columns. All right, and this thing is what's called a multi-index, which means that there are actually a hierarchy of columns in this data frame. You can think of this hierarchy of columns as being like layers in a three-dimensional data frame. So we have row labels, and then we have major column labels and sub-column labels. So the major columns are adjusted close, close, high, low, and volume. Oh, open and volume, sorry. So, prices and volume information. And then the sub-columns are the actual stock tickers that were that the data is contained in. Okay? Or that the data pertains to. So we can now, okay, so I just said this information on slide 5. We've got column names and sub-column names. If we want to see the closing prices of the stocks, we can say stock price sub and then give our column name. This is a major column name. And, stock prices, sorry about that. Stock prices sub close. What did I do? What's the name of this variable? Stock data. My apologies. So stock data sub close. There we are. And so here are the closing prices for the various stocks. And since I've chosen a large font that's easy to read, I'm not actually seeing all of the closing prices for all 4 stocks. I'm just seeing Apple and U.S. Steel and Cisco and Cisco and Goldman Sachs are hidden. All right, now this thing as well, stock data sub close, is also a data frame, which I can see if I ask for its type. So this is a 2-dimensional data frame in which there's only one set of columns. In other words, if I say stock data sub close dot columns, now the columns are just a regular index with the ticker names: Apple, Cisco, Goldman Sachs, and U.S. Steel. Now let me create a variable stock close to refer to these closing prices so that it's easier for me to access that information. So I'll do that. Stock close gets stock data sub close. Okay, there we are. Now let me, generally speaking, stock prices are not quoted out to, 6 decimal places. Let me round this information to 2 decimal places. And not only does that get us prices that are more like what we expect to see, but also we're able now to see all 4 stocks: Apple, Cisco, Goldman Sachs, and U.S. Steel. Okay, so stock prices are all very nice, but we're typically more interested in the rate of change of these prices over time. And one of the cool things that the data frame data type provides to us is a percent change method. So if we have time series data like we do here, we can use the percent change method to get the percentage change from day to day. So let's give that a try. I'm going to ask, so we've got stock prices, or stock close, I should say, which we've displayed for convenience rounded to 2 decimal places. And so I can compute daily stock percentage returns by asking for stock close dot percent change. Okay, and here we have the returns, and I'm going to round these to 3 places so everything will fit on my window. Okay, excellent. So these are the daily, that is on a trading day basis, the daily returns of these stocks. We can plot this information by using a package called matplotlib. And this is something that you'll have a chance to play with in a couple of homework assignments. Matplotlib is a big, huge, complicated mess of a module. It does have official documentation that is very difficult to read. And so your best bet as far as understanding how to use Matplotlib is Google and looking for examples on places like Stack Overflow and so forth. But let me just copy in and give this plotting stuff a try. What we want to do here is to produce a plot of percentage returns per day. Let's give this a roll. I'm going to import Matplotlib as MPL. All right, I'm going to copy and paste that so I don't have to type, and then import matplotlib's pyplot module as PLT. And then I'm going to produce a plot, or generate a plot, I should say, by using the .plot method for the data frame. And I get told, okay, something was created. Now, the plot is not automatically displayed, which means that you can continue editing and tinkering with the formatting of the plot and the various labels on the plot and so forth. When you do finally want to see the plot on your screen, you say plt.show. And conveniently, apparently, nothing happens. Well, actually, this does display the plot on the screen, but for some strange reason, the plot is actually hidden behind the idle shell window. So you'll have to look down at your taskbar and locate typically the blinking icon to display the plot. All right, and here we are. So here's the plot. So this shows the percentage returns of these 4 stocks from starting from January 3rd. Okay, so that's the percentage return relative to January 2nd, and then extending through January 22nd. You'll notice here that the shell itself is hung now, waiting for this plot to no longer be displayed. So I'm going to close the plot, and my shell will come back to life. Okay. Now, there are other built-in statistical evaluation techniques that are built into pandas, to the data frame type, such as the correlation and covariance between different stocks. So, for example, here is all of the stock rets, but if I only want to look at Apple, I can just ask for that particular column, AAPL. All right, so here are the daily stock returns for Apple. Now, you may remember, and this is what's shown in slide 10, that if the column name does not have any spaces or mathematical symbols or anything like that in it, you can also display or access a particular column in a data frame just by typing the name of the column. So stockrets.apple as opposed to stockrets sub and the string apple will give me that same information. And let's have a look, for example, at the correlation between Apple stock and Cisco stock. Okay, there's a fairly high correlation. Well, you know, it depends on what you mean by high. 0.87 is, you know, closer to 1 than to 0. So it's not too shocking, I guess, that two technology stocks would be rather correlated. But if I were to compare Apple to Goldman Sachs, okay, the correlation there is much lower. Now, this correlation may strictly be due to market fluctuations. You know, if the market is moving up, then stocks that are going up will appear to be correlated, even if in reality they're not too correlated. We can display covariance as well. So here are the covariances between Cisco and Goldman Sachs. Okay. In addition to those, we can ask for all the correlations or all the covariances by just using core or cov directly on the data frame with no arguments at all. This is going to produce a correlation matrix between all of the columns. All right, and so here we see, as we would expect in a correlation matrix, that every stock is perfectly correlated with itself, so the diagonals are all 1. And the correlation between Apple and Cisco, as we saw, was 0.87. Apple and Goldman Sachs, Apple and US Steel are much more low correlation. And the lowest correlation that we have actually in here is between Goldman Sachs and Cisco. All right. And of course, this is a symmetric matrix because the correlation between Apple and Cisco is going to be the same as the correlation between Cisco and Apple. Here are the covariances. Or at least it would be the covariances if I could type properly. So let me do that again. Okie doke. Now, rather than dealing with percentage returns, models of the evolution of stock prices generally work with log returns instead. That is, you take today's closing stock price divided by yesterday's closing stock price. That's going to be a ratio of 1 if there's no change in the stock price. It'll be above 1 if there's an increase in the stock price, and below 1 if there's a decrease. And then the log of that ratio will be 0 if there was no stock price change. The log of 1 is 0. Otherwise, if there was a positive increase in the stock price, the log will be a positive number. And if there was a decrease, the log will be a negative number. Okay? So we compute the ratio of today's prices relative to yesterday's prices, and then ask for the log of that value. We're furthermore going to make an assumption that these log returns are normally distributed with some average return mu and some standard deviation of returns sigma. This turns out to be mathematically much more convenient to deal with than daily percentage returns. Other people are going to explain this to you over and over again in other courses. I'm just going to ask the question, does this model make any sense? That is, are log returns actually normally distributed based on this tiny amount of data that we're looking at here? Now, if the log returns are normally distributed, then the skew should be 0. That is, this distribution of log returns should not be lopsided to the left or the right. And also, the so-called excess kurtosis should be 0. So the kurtosis has to do with how thick the tails of the distribution are. A normal distribution has a kurtosis of 3. What we're computing here is the excess kurtosis above 3. If the excess kurtosis is positive, that means that the distribution of these returns has actually got thicker tails than a normal distribution. And if the excess kurtosis is negative, the distribution has thinner tails. Thicker tails, by the way, are a really good way of losing a fortune. So something to be concerned about. Okay, so let's analyze log returns and have a look at whether, at how to compute them, A, and whether we see evidence that this makes sense, B. So in order to compute, let me back up a second, we need to compute this ratio of today's price divided by yesterday's price. How can we take the stock closing price data frame that we have and compute this ratio of today's price divided by yesterday's price. Well, it turns out that there's this cool, I guess it's cool, uh, method in data frames that you can use for shifting a time series forward or backward. If I shift a time series forward by 1, notice then that all of the prices for the stocks are shifted forward by 1 day. For the first day, for January 2nd, in the shifted data, we have not a number of values. And for January 3rd, we have what were the January 2nd values. For January 4th, we have what were the January 3rd values, etc. So in a nutshell, stock close is today's prices for each day in the time series, and stock close shifted by 1 is yesterday's prices for each day in the time series. And we can simply, therefore, divide the stock close data frame by the stock close shifted data frame, and that will give us the ratios of today's stock prices to yesterday's stock prices. Let's give that a try. So here's stock close. Rounded to 2 places. Here's stock close shifted 1 day, rounded to 2 places. Stock clost. Well, not too far off. Okay. Stock close. And so if we divide, if we say stock close over stock close dot shift 1. All right, so there we have the ratios of today's return for divided by yesterday's return for all of our dates in our range, except of course for the first date. So for January 2nd, we don't in our data set have a record of what the December 31st price was from 2018. And as you can see, as I said, these values are pretty close to 1. Some of them are a little bit above 1. Some of them are a little bit below 1. And so we can take the logs of these things to get log returns. So that will be our next step. And let me just cut and paste that long expression. So this is our log returns. Log is natural log, so we're getting the natural logs of these ratios. Whoops. Okay, I need to use the log function from the NumPy module. I need to import NumPy and do that as np. And Shazam. So now, here are our log returns. Okay, and these numbers are all quite close to 0, as we would expect. Some of them are slightly negative, some of them are slightly positive. I'm trying to see if we have any exact zeros. Okay, so there's no stocks in here whose price didn't change at all from one day to the next. Otherwise, we would have a log value of 0. All right, we can display a plot of these values using the same code that we did before, but this time using log rets instead of stock rets. So I can just say, I've already imported my matplotlib stuff, so I can just say log rets dot plot title equals log return I guess it's okay. I guess there's no S. My mistake. Okay, so the plot was generated, and now to display the plot, I have to say plot.show. And there it is. This time, for whatever random reason, it did not show up behind my my Python shell window, so I have it right here. And it's a tiny bit different shape from the percentage returns, but not really. I mean, clearly it looks the same. I mean, the log returns visually are not too different from the percentage returns. Now, so the next question we're going to ask is, are these log returns normally distributed? Well, we can use the mean function to get the means of these log returns for each stock. Okay, and we can use the std function to get the standard deviation of the log returns for each stock. So Apple, during our brief period of time, has got a slightly negative return. Of these stocks, Goldman Sachs is performing the best, again, during this very short period of time. From looking at the standard deviations, we see that Apple and U.S. Steel were more volatile than the other two. So that's useful information, the mean and the standard deviation. Doesn't tell us anything about whether these distributions are normal or not. So let's take a look at the skew and the excess kurtosis. Logret.skew. Now the skew should be 0 if this is actually log normally distributed. And these are not really all that close to 0. I mean, I guess it depends on what you mean. We have such a tiny amount of data in this time window that we maybe should really be pretty suspicious that these skew values are meaningful at all. If we wanted to test whether the skew was significantly different from 0, we really ought to look at a much longer period of time than just 15 or 20 days. Similarly, we can look at the excess kurtosis by using the KURT, K-U-R-T method. And you'll notice that these things are significantly larger than 0, indicating that at least during this very brief period of time, which again is probably too short to give us meaningful results, that these distributions have much thicker tails than a normal distribution. Now, what's wrong with that? Well, what's wrong with that is if you do make the assumption that log returns are normally distributed, and you then use various equations and formulas to compute future stock prices and therefore future option prices, if the distribution is in fact more widely distributed than normal, that is, if the tails are thicker, that implies, among other things, that you are more likely than normal to have a negative result in comparison with what your model claims. So this is something to be concerned about, and something that you'll be informed about in multiple classes as your program progresses. All right, so that gets us to the conclusion of this stock analysis material using pandas data frames.